Hey everyone, I'm Nate Strout here at the University of Redlands at the Center for Spatial Studies. Welcome to this tutorial on using raster analysis tools to model wildfire risk with GIS. So first of all, we're going to be going through a model of wildfire risk, but this is not meant as an authoritative risk model by any means. It's really meant as an instructional tutorial to demonstrate some raster analysis tools. But a lot of the criteria we'll be using, a lot of the data that we'll be using would be used in a real fire model like this. So those will be slopes. We'll be looking at the steepness of slopes. We'll be looking at the type of land cover, whether that's forested or urban. We'll be looking at proximity to roads, visibility from fire lookout towers, and then the aspect of slopes, so the direction that the slopes are facing. So let's dive into this here. Okay, so this is a companion video that goes along with a written tutorial that you can download from the link there. So the first steps will be to go ahead and set up that project and download the data. Most of you have already probably gone through this process, so we'll whip through this pretty quickly. Remember that creating a new Pro project also creates a new folder with a new APRX file, that's your project file, a new geodatabase, and a new toolbox in it, ready for you to use for that project. So when we download the data for this tutorial, we'll want to put it in that same project folder so that we can find it easily. And of course, we'll need to extract that zip file with all the data in it because ArcGIS Pro isn't going to be able to work directly with that zip file. And then one more piece of setup here, we want to change the coordinate system for this project. Right now it's set to Web Mercator because the base map's in Web Mercator, but I want to use UTM NAT83 Zone 11 for this project. This will be a better coordinate system to use because the coordinate system is localized for Southern California, and it's meter based, so we'll be able to interpret what the cell sizes are a little bit better for this project. All right, so next we're going to do some kind of data processing steps to get started here. So elevation will play a big role in this project, and so I've provided some data from the shuttle radar topography mission. This is elevation data collected from the shuttle. And it's kind of the de facto standard for elevation data. This data is provided in tiles. You can see there's 33,117, 33,118. So those are like full degree tiles between each one of these. But when we're doing the analysis, we're going to want to put these together into one big image, one big raster file that we can work with as a single raster. So to do that, we're going to use the Mosaic to New Raster tool, which is a geoprocessing tool and can be found over in the geoprocessing pane. I'm going to go ahead and browse to it for now. I highly recommend browsing to tools rather than just searching for them, especially when we're getting started, so you can learn about what other tools are available to you in the toolbox. So here's the Mosaic to New Raster tool. You can pick them from the list here, or you can drag them in from the contents. I'll go ahead and drag these in, holding down Shift to select them. And then we need an output location and a new name. So we're going to put this in our geodatabase for this project. And we're going to name that the SoCal_DEM. Spatial reference we'll leave for now. We do want to change this to 16-bit signed. If we hover over this I, we can learn what those mean. Essentially, it's how big the numbers can be that are stored in each raster cell, similar to a field data type in vector data. And this is just a one-band image. Cell size it'll figure out by looking at each of the individual cell rasters. So everything else is ready to go here. So I'll hit run. These other two parameters that we left as default would handle if there are any overlaps among the rasters. We don't really have any overlap in ours, but most rasters would have some kind of overlap, so it'll let you deal with that. Okay, so this is done here, and you can see that we now have a seamless DEM. This is one big raster. I'll go ahead and turn off these other ones so you can see that we just have one big raster file now. And I'll go ahead and remove these individual ones just to avoid any confusion. So this is all, this is great. We've got this as one big file. But when we ran this, it kept the same coordinate system as the inputs. So these are all in WGS 1984. I'd rather have those in UTM. So we're going to use a tool to do that. That's going to be the Project Raster tool. That's also a data management tool. And here's the projections and transformations tool set. This is a raster, so we'll work in here. And here's the Project Raster. We'll pick this as the input. We'll give this a new name of SoCal DEM underscore UTM. And then we'll pick the coordinate system that we want. Because we already set it for the map, we can simply select that, and it'll know that that's in UTM Zone 11 and set the transformation method for us, all this fun stuff. We do want to change this from nearest neighbor to bilinear interpolation. Basically, when it's, now we can go ahead and run that. Basically, when it's moving the pixels around, it will need to kind of estimate the values of some of those pixels because they're aligned differently. And bilinear is a better method to use for continuous data like elevation or temperature. Some of the other methods would be better for discrete data like land cover or something like that. So that's done. Not really immediately clear what happened there, but I can show you that if we look at the spatial reference, this will tell us this one's in WGS 1984. And we can see that in that, the cell size is 0.00027 degrees, right? Because WGS 84 is geographic and therefore the units are degrees. But when we look at the coordinate system for this UTM one, we can see it's in zone 11, which the linear unit is meters. And when we look at the raster information, this is roughly 30 meters, a 30 meter pixel, roughly. All right, so I'm going to go ahead and remove this one. So we're just left with the UTM one. All right, so the next thing we're going to do is work to define a study area. Study areas are pretty important with all GIS projects, but especially with raster projects, because we can really cut down processing time by getting rid of all the pixels that we don't really need. If we process all these extra pixels, it can add a lot of processing time. So this study area here, I'll change the symbology so we can kind of see the area we're looking at. These are the Southern California mountains, mountain ranges, kind of our study area here. This is where we expect to see most wildfires. And it kind of hugs highways and major roads here. However, I do want to include some of the criteria of the area just outside of our study area. If we just limit this to directly inside, we can get some what are called edge effects. And so we want to minimize those by actually making our study area just a little bit bigger than the area we're actually concerned with. So to do that, this is a vector polygon, so we can go ahead and use a buffer to do that. And we've done that a few times here. That's going to be an analysis tool that is, analysis tool proximity buffer. And I'll just take the study area, give this a new name of study area 1 kilometer. And we'll go ahead and set that here. We can take all the defaults and we'll take a look at what that looks like. So you can see that that buffers out just a tad so that we can include the effects of the area just outside of our study area. And I'll remove this original study area just so we're not confused by that area. All right, so we have our study area, and we have this much larger DEM. So let's go ahead and cut this DEM using the study area, kind of using that study area as a cookie cutter for this. So that might sound familiar with vector data. We would have used a clip tool to do that. But with raster data, we have a slightly different tool. And for that, we're going to go down here to the Spatial Analyst toolbox and find the extraction tool set. So we're going to extract this piece out of the larger data set. A bunch of different extraction tools here. The one we want is extract by mask, which is a great one for if we have a vector data set polygon that we want to just use as the cookie cutter. That's the one to use. So the input raster is our DEM. The study area, the mask is our study area, and our output will be called DEM underscore study area. And when that's done, we finally have our elevation data set up for us. We've done a few steps here to get it exactly right, but we have our nice clipped DEM to our study area. And we'll go ahead and remove this SoCal one. We're not going to need that anymore. All right, so now we can start looking at the actual criteria for our model. And the first one we'll look at is slope. So what is slope? Slope is just the steepness of the terrain. So for every 30-meter pixel in our elevation, we'll get a sense of the steepness of that slope. There's a tool to do that. It's really easy to do with a DEM. We can find that in the Spatial Analyst tools in this surface group here. And here is slope. So we'll just tell it that the input DEM is our study area. The output raster we're going to call slope underscore study area. And we have the option of outputting this with degrees or percent rise. We're going to use percent rise for this example. We can go ahead and keep the other defaults. So this should run pretty quickly, and we now have for every cell, we have the steepness of that slope. So the darker cells are going to be steeper than the lighter ones. So we have some flatter areas down here in the valley. Lakes are going to be completely flat because it has one elevation value, and then you can definitely see the darker areas are the steeper slopes up in the mountains. We're going to change this symbology just to a different type of ramp here, or different kind of color scheme here. There is one called slope, so to see that, I'll click the show names and we'll go find slope down here. Just give a little bit different sense of the slope. The kind of reds pop out a little bit better. And then we're going to do one more step here, and that is to kind of smooth this out a little bit so that if we just have a small 1 pixel or 2 pixels that are surrounded, steeper pixels that are surrounded by flatter pixels, we can kind of discount those. Those aren't really going to be that important to our analysis in this case. So we're going to use a focal statistic to do that. That statistic would just be to get the average. So for every cell, we're going to actually look at the average slope around that cell to come up with the actual slope for that. So it's going to, in essence, smooth this out a little bit. So that's also here in the Spatial Analyst Tools toolbox. And we're going to look, this is a neighborhood analysis. And so we have a few other ones we can use here, but we're going to use the focal statistics. And for this, we're going to use the slope as input. And we're going to rename this slope underscore focal mean. And we're going to keep these defaults, but just notice that you could change what the neighborhood is. We're going to use a rectangle, a 3x3 rectangle around each cell, but we do have these other options. And we're going to use the mean, so the average statistic. So for each cell, we're going to find the average of the cells around it, but we could use these other statistics as well. Go ahead and run that. Oh, what? Named this wrong, didn't I? Slope underscore focal mean. And this has a different color ramp, different color scheme attached to it. I'll go ahead and change that quickly. This won't be exactly head-to-head comparison between the two data sets because one uses a classified ramp, but you'll kind of get the idea. Right, so it kind of smooths out that surface. And so this is the one we're going to use for our analysis here. And okay, so now we know what the slope is for every cell, whether it's a steep slope or a flat area. But we need to kind of convert that now into something we can use to evaluate fire risk. Right? So we kind of have to pick a threshold at which the slope is considered high risk or low risk. In this entire model, going forward, we're only going to look at whether it's risky or not. So we're going to have a risk is a 1 or a 0 across the board for the rest of the model. We'll look at more complicated models in future lessons, but we're just going to look at whether it's a risk is a 1 or a 0 in this case. We just have to pick a threshold, and in this case, that threshold is going to be 30. So anything greater than a 30 slope would be considered risky. So this is going to be a really simple analysis here. We're going to use a tool called greater than equal to, right? So think of that kind of as an operator, right? The alligator eating the the bigger number. So that's going to be a math tool. It's actually a logical math tool. So there's other math tools in here like plus and divide and minus. So think of those as other operators that we could use if we need to add these together or something. But we're going to use the greater than equal tool here. And we're going to use the slope focal mean. And the number we want to look at is 30. So we're going to say if the cell is greater than or equal to 30, we're going to give it a 1. Everything else will get a 0. And that's how this tool works here. So this we're going to call a risk underscore slope. Now you could imagine, instead of just using a 1 or 0, we could probably come up with some more a gradient for that. We could say that 30 is a little bit risky, and 50 is much more risky. We'll obviously look at that in future lessons, but this one we're just doing a 1 or a 0. So here's what our output looks like. You'll notice we have a 0 and a 1. I'll go ahead and actually hide this 0 just by giving it no color, so we can kind of see where we're expecting to see more risk based on slope. So these are everything greater than or equal to 30%. Notice that most of the valley just kind of disappears because it's flat down there, and we don't expect to see wildfires on flat cells. So the next criteria we're going to look at is roads and the proximity to roads. The idea being that fires, whether intentionally or not, are often set near roads, kind of a human access proxy. So let's go ahead and we'll pull on the roads layer here, and I'll turn off the slope risk here. Now this data was downloaded from the Census Bureau, and data is delivered in county pieces that you can download. And I've just gone ahead and put those together here. There's about 400,000 lines in this data set, and you can see it's goes quite a bit beyond our study area, right? So we want to limit our analysis down to the study area, which we'll look at here in a minute. So we're going to run a tool called Euclidean distance. Now this is another spatial analyst tool. You'll find that most of the actual raster analysis tools are going to be found in this toolbox. So this is a distance tool. It's actually considered a legacy tool at this point, but we're going to go ahead and use it. This Euclidean distance, right? So it's just going to calculate the distance of each cell to the closest road in this case. So the input raster or feature data source, we have a feature data source here. We have these roads. The output we're going to call roads proximity. We don't have any barrier data. We're not going to set a maximum distance. We want to use 30 meters as the output size. So 30 is going to be the output size, so it roughly matches our other data sets. And we'll go ahead and keep the planar. We do need to switch over to this Environments tab and do a couple of things over here. Again, the Environments tab is available on all of the tools, and these are settings. They're different parameters that are available that you could set for all the tools, but you generally don't. You usually keep the defaults. And to include them all on this page would just make for a very long page to fill out, especially when you don't usually set them. So you could keep it on a separate tab. So we're going to set the output coordinate system because we want, even though these roads are not in UTM, we want the output to be in UTM. So that would save us a second projection step. We're going to set the processing extent. So we're going to limit the extent of the processing to our study area. We're going to set a mask as the same as the DEM, of the study area. And we're going to set a snap raster. So snap raster means that we're going to snap the pixels. We're going to align all the pixels together to the DEM study area. So so this will mean that the pixels directly overlap each other. So when we're doing raster analysis, we're doing overlay analysis, they'll be lined up properly. So I think we're ready to go here. I'll go ahead and hit run. This can take a couple minutes, so I'll go ahead and speed the video along. So that didn't take too long here. We can look down here and see it took 32 seconds on my machine. It might take a little bit longer on yours. And you can see the result here. It's underneath the roads right now. I'll go ahead and turn those off so we can kind of see it a little bit better. I'll also change the appearance here to a different stretch type. We're going to set the standard deviation here, which is a little bit easier to see what's going on here. So I'll zoom in here, and if I click at any one cell, and you can start to see as I zoom in here, you can see the individual cells here. So each one of those is 30 meters, and this number that I'm getting here is the distance to the closest road. So there's the closest road, and we're at about 426 away. So that number that we're seeing there is in meters because we're using a meter-based coordinate system. If this was in WGS 84, those would be in degrees, which wouldn't mean a whole lot, right? So, so again, we have kind of the same issue that we did with slope, is that we know the distance for each cell, but we need now to calculate a risk level. So again, we just need a threshold. And in this case, that threshold is going to be 1 kilometer. That's what we'll use for this. So if we're within a kilometer of a road, we have road proximity risk. If not, we have no road proximity risk. So let's go ahead and do that now. We're going to use a very similar tool that we did last time, which was the greater than equal to. We're just going to use one called less than here. So that's, again, a math logical tool, and here's our less than. We'll use the roads proximity as input. We'll set this to 1,000 because it's meter based. We want 1 kilometer. And we'll call this risk underscore roads. Hit run. This again is calculating a 0 if it's greater than 1,000. The number is greater than 1,000, and a 1 if it's less than 1,000. Easy enough to understand there. I'll go ahead and remove the blue so we can kind of see it. And in fact, I'll use the appearance slider here to kind of see where we're talking about. So the red now is where we would expect to have risk due solely to roads, right? So it says we have a lot of high risk wildfire areas in the valley where it's flat. We don't; those will kind of get reduced when we combine it with slope, right? So the areas that we're really concerned with is where do we have high slope risk and high roads risk, right? Along with the other parameters that we'll look at. So I'll kind of use this transparency slider here, and we can maybe start to see where those areas overlap a little bit. All right, so next we're going to look at land cover. Land cover essentially it's the physical surface of any cell. So that would be whether it's forested, whether it's paved, whether it's water, whether it's rocks, whether it's cropland or whatever it might be. This is in the United States. We can get this for every 30 meter pixel. We would know the land cover. I provided a link to a site here. Each pixel has a number associated with it, and each one is the code for a classification. So you can see that 21 through 24 are all developed. Forested areas are in the 40s, shrubland, herbaceous, and a bunch of different types here. So you can imagine that some of these are going to be more risky in terms of wildfire than other. So if we look at the attribute table here, we can kind of see those as well. So we have the value here is that code that we were looking at on that website, and the description here is listed in this land. The color that you're seeing here is all built out of this red, green, and blue fields here. So the red areas here are going to be your developed areas. Some of these other colors are going to be either forested or shrubland, or blue is obviously water. So it has kind of a color scheme built into this. And if you click on any one cell, it'll tell you what the code is, 52, and the type is. So we basically just need to take these values that we get, which are those different codes, and reassign or reclassify those values to a risk number. So water is obviously going to be 0. We're not going to burn on water, so that code is going to be 11. And in a forested area like one of these over here, 42, in an evergreen forest, those are going to be a riskier, a number 1 in our risk surface. So let's go ahead and do that now. The tool we're going to use for this is called Reclassify. That is also a spatial analyst tool. Go down here to the Reclass group. Here's Reclassify. We have a few different tools here. We'll just use this Reclassify tool. Let's take our NLCD data. Sorry, I should have said NLCD is the National Land Cover Data Set. And it's put together by scientists from a number of agencies, including USGS, Forest Service, and others, and using satellite imagery to classify every pixel. Okay, so we've got our Reclassify set up here, and we need to fill in these values here. So if we click unique, it'll fill in. These are each one of those values. And we have the current value and the new value that we want to set it to. These are obviously not correct here. So we need to go through and kind of individually assign these. So 0 is no data, right? 11 is the water, if you remember. In the 20s, we're talking about developed land, which we're not going to consider for wildfire, so we're going to set all of those to 0. And all the way down to 31 will be 0. In the 40s and 50s, we're talking about vegetated land. And we're going to go ahead and set all the way down to 81 will have a risk value of 1, and these other ones will be zeros. If you want to refer back to that sheet, to this website, you can see what each one of those are. And these are purely based on Nate Stroud's assumptions about wildfire. There's no, this is not based on any real science. And so we'll go ahead and rename this risk land cover. We'll change this change missing values to no data. We'll set that. That really shouldn't be an issue for us in this case because we've set all of the values. We do need to jump over here to the Environments tab and set a couple of things. First of all, NLCD is not provided in UTM because it's national, so we want to set that. We'll go ahead and change the extent and the mask to use our study area. And we'll go ahead and set the snap raster again as the DEM, just so that those pixels all get aligned nicely. And we can run this. So pretty quickly there. And we can see, I'll go ahead and once again turn off the 0 so we can kind of see the areas that are going to be considered risky in terms of land cover. Right? So again, we're up in the mountains here. Anywhere that's going to be a fuel for a forest fire is going to be have a value of 1 here. Okay, so again, let's kind of just compare that to. We'll look at our slope. We'll compare that to slope here by using our transparency slider and just see where we have overlaps in there. So we should be able to see the greenish slope color with our risk, our land cover risk as well. So anywhere you're seeing that through. All right, so we are making our way through these criteria here. We're going to move on to aspect. So aspect is the direction that the terrain is facing, the direction of the slope, whether it's north, south, east, or west. So we actually get a compass bearing direction for each cell, and that's which direction that slope is facing. In terms of fire risk, we're looking at this because, at least in the northern hemisphere, the slopes, the southern facing slopes, are going to have a higher risk of wildfire because they're getting more sun and therefore are drier, more combustible fuels on those slopes. So slope is another derivative of a DEM, of elevation. So we're going to go find the aspect tool here. That's with surface, where we found slope earlier. Here's aspect, and we're just going to use our DEM as the input raster. The output is going to be aspect underscore study area, and we'll go ahead and use this planar method here and hit run. So we get this pretty funky psychedelic looking output. If we take a look at what all those colors mean, you'll see that like the red is a northern facing slope, kind of the bluers are south west and northwest facing slopes, and so on. So it's hard to come up with a color ramp to show all of those different values. But if we zoom into one of these areas, I think it'll be kind of clear. So these more red colors here, these red aspects are the northern facing. These bluer, yellower ones are southern facing. Sorry, I'm colorblind, so if those were completely wrong, I apologize. And so in the middle would be kind of the ravine between those, the valley between those. So we have, these are facing north, these are facing south. And then the idea is that these are going to be the higher risk in terms of wildfire. And I've actually gone ahead and made a scene out of this real quick, which I think helps make that point a little bit clearer. So this is in 3D. We have the southern facing slopes here and the northern facing slopes here, right? See that pretty clearly. So we're going to do another reclassify operation here, but this time instead of changing individual values like we did with the land cover, we're going to change ranges of values. So we'll go ahead and drag in the aspect here, and the ranges, we have a start and an end value here, which correspond to how these are classified in the catalog and the contents pane over here. So we can set these ranges. We can use these, or we can enter new values. So that's what we'll do. So we're going to set this so that the southern facing slopes of 112.5 to 247.5 are set to 1, and everything else is 0. So we'll go ahead and do that here. We'll use -1 to 112.5, and we'll set that to 0. And then from 112.5 to 247.5 is 1. And then from 247.5 to 360, we'll set that back to 0. For all these other ones, just click on in the row, and you can hit the delete key and get rid of all these. We can keep the no data value here. And we're going to call this reclass. We're going to call this risk aspect and run this. We don't need to set all the environment settings this time because this is all based on our DEM, so it's going to use all those same pixel sizes and the mask and all that. So here's what that result looks like. You can see, so 0 is on the northern facing slopes and 1 is on the southern facing slopes. The last criteria we're going to look at here is the visibility of lookout towers in the mountains. So there's still a lot of lookout towers up there staffed by volunteers, and they're credited with stopping dozens of wildfires per year. So we're going to look at which cells can be seen by a lookout tower. And to do that, we're going to use a Viewshed analysis. But there's a little setup we need to do first. So first of all, I was able to find a table of where all of the lookout towers are in California, actually. There's a spreadsheet we can download. I've provided that with the exercise data there. That includes a name, some location information, including a latitude and longitude. And so we can turn that into points and use that in our analysis here. So let's go ahead and turn this into points by right-clicking on it. We'll go to export to a point feature class. We're going to name this lookout towers. And it already recognized the longitude and latitude fields here. And the coordinates that are given are in WGIS 1984. And we'll go ahead and keep them as that WGIS 1984. But keep in mind those will be in a different coordinate system than our UTM. Okay, so now we have a point for each of the lookout towers in California, actually. Now we're obviously only concerned with kind of our Southern California area, so we'll deal with that later. But now we can start working with the Viewshed tool. Now, Viewshed tool is nice because we can set some additional properties about each location to say how high it is off the ground, right? So by default, it's actually, it assumes the observer is on the ground. So for a human observer, you might have it set at about a meter. For the lookout towers, we're going to set those to about 10 meters. We can also set some other settings like how far the observer can see. And we're going to set that to about 20 miles for each lookout tower. Pretty far, but that's kind of the effective distance that I found for these lookout towers. So the way that we do that is actually put that information in the feature class as fields, in the point feature class as fields with that information. So each tower could be at a different height, and it could potentially be a different visibility distance. We don't know those for each individual tower, so we're just going to set those, set the same value for each tower. And we do those with some specially named fields. And this is all in the documentation for the tool. But I'll give you the two that we're going to use right now are offset A. So that offset is the offset of the from the ground to the observer, to the height of the tower, and then radius 2. That's going to be the distance that the observer can see. So go ahead and add those fields. They can both be long types. And then we're just going to use the calculate field tool to calculate those two values. So, and these distances will be in meters because our coordinate system is in meters. So we're going to calculate this field. Just right click on it, calculate, set the offset A to 10. Make sure nothing's selected here, so we run it on all of our 506 points. And we're going to do the same thing for radius. And 20 miles in meters is 32,187. So apply there. All right. So again, if we had individual heights, we could put them in here, but we're just going to assume they're all at 10 meters off the ground. Okay, so we have our data all set up, but keep in mind we have points for all of the points for all the lookout towers in Southern California. We only want to run it within our study area. So you might remember that when we're running geoprocessing tools, generally we can filter, we can limit the number of features being used in that process by doing a selection. So we can use our select by location to select the lookout towers that are within our study area. Okay, so it just selects these here. And now we can use our visibility tool, our Viewshed tool. So Viewshed is another one of those spatial analyst tools. So we have a spatial analyst. Look, that's a surface tool, and there's Viewshed there. So there was slope aspect. We went Viewshed now. The input raster is our elevation. So I'm going to go find that. This DEM study area. The input observers are our lookout towers. We're going to name, and it's only going to use the selected ones. That's assumed in this. And then the output raster we're going to call tower visibility. And then let's switch over to the environments tab. We have to set a few of those here. We're going to set the output coordinate system to be the current map. We're going to use the mask of the study area. and we're going to use this, well, we don't have to set the snap raster, but I'll go ahead and use it anyway. The study area. Once that's all set, we can go ahead and run it. This does take a few minutes, so once again, I'll skip ahead. Okay, so here's our output. So what we're looking at is the darker cells are those that can be seen by more observers. Right? So these lighter ones can be seen, but just by one tower. And for our analysis, I think that's fine. As long as you can be seen, each cell can be seen by one observer, we're just going to call that not as risky. Anywhere that can't be seen by any towers is more risky. Now, they're not really clear in here which ones can't be seen by any tower. The areas you can kind of see through that are transparent. In fact, if I click on one of these cells here, it says that the tower, that it's 0. The value is 0 right here. Notice that 0 isn't actually included in our color scheme here. So you're not seeing it, but the cell values are 0. So, in terms of fire risk, we want to set anything that has a value of 0 to a 1 risk value. Anything else, so if it's anything from 1 to 11 here, we can assume that that has a 0 risk in terms of tower visibility. Now, we could use the tools that we used earlier called equal to, greater than, equal to, those kinds of tools. I'm going to use a little bit different tool here called the raster calculator to do that same thing this time. So the raster calculator can be found in this map algebra group here, and spatial analysis map algebra. And this tool is really, really powerful. We can treat each one of these rasters as an input into a mathematical expression, so that it will do that expression for every cell in our entire raster. So in this case, we're just going to use that equals operator to say where the tower visibility is equal to 0. So I'm just going to say tower visibility. You can type it, or you can double click the rasters up here. Type equals 0. Spacing doesn't matter in this case. Actually, sorry, we need to put 2 equal signs here. Equals equals. So 2 equal signs means is equal to in this case. And we'll name that risk underscore towers. Okay, and hit run. So now we're getting this new output where 0 can be seen by a tower and 1 can't be seen by a tower. I'm going to change this color here so that we can see these a little bit better. And we can see the locations that cannot be seen by a tower now. Right? So if we start comparing that with some of our other risk, we'll look at aspect here. Let me turn off that one too. And start using that transparency slider. We should start to see where those two overlap, right? So that would just be looking at 2 different variables at a time. Next, we'll combine all of these together. Now, to combine all these and come up with kind of a final risk layer, all we want to do is add the values of the cells up for each cell. So if we have a risk value of 1 in a cell for each of our layers, we would have a value of 5. If it's just 1 there and all the rest are 0, we just have a value of 1 there and in between. So where we have a higher number, we'll have a higher risk. Pretty simple analysis here. So because we're just adding things up, let's just use that raster calculator we were using a minute ago. I'm going to clear this out here, and let's just take our different risk layers. So I'm just going to say this one, and we put a plus sign, plus the risk aspect, plus the risk land cover plus the risk roads plus the risk slope. So we should have 5 there. 1, 2, 3, 4, 5. We'll come up with our final risk. So I'm going to call this the risk sum. So it's just going to add up the values of each cell for each one of those rasters. And I'll go ahead and run that. All right, so that's our result. It's not using a very good color ramp here. I'm going to turn these off, and let's change this color scheme here. So we're going to go to the symbology. Instead of using unique values, let's use a... Oh no, we can leave that. Let's change this to a prediction ramp. That's what I kind of like. So from a blue to a red, with kind of a yellow in the middle. All right, so the blue cells here have 0 risk across the board. They were all zeros. And one had 1 risk criteria there, and all the way up to 5. So this area here has all 5 of the different risk indicators had a value of 1, right? So that's pretty close to what we want. I mean, although we're ending up with a lot of kind of mid-range values here in the valley, which don't make a lot of sense, right? I mean, it's because there were roads there. Maybe it had a little bit of a slope to it. The aspect might be right, so some of those are still coming up as a value greater than 0. So we can be a little bit smarter about this by treating the land cover as an exclusion. So if the land cover is one that isn't going to burn, if it's water, or if it's a developed area, it's not a wildfire risk. So we can exclude that. So so let's take a look at, let's do this analysis again, but instead of using land cover as just another criteria to sum up, let's multiply it by that. So if, regardless of what these values are, so if we add up all these and we multiply it by the land cover risk, if that land cover risk is 0, so if you take all these and then multiply it by 0, the result's still going to be 0. And otherwise it's going to be multiply all those by 1, and so we'll just get the same result. So I use parentheses here, just like you would on a calculator, to do these first, times this land cover risk. And we're going to change this name to kind of a final name of risk wildfire. Run. Great. So let's change the symbology again here. Just change the color scheme to prediction. All right, so this is a little bit better, right? So all of these cells kind of in the urban areas down out of the mountain ranges are zeros now. And we can pretty clearly see where we have higher risk. All right, so this is kind of our result here. We might want to evaluate why these which these are all set, like these are 2 and 3 criteria, but if we want to know which one they were, which is a common thing, it's not just the final result, but you want to kind of interrogate your results. One trick you can do is turn on all of the layers underneath this final one here. So turn on all of the risk layers. I'm going to turn on the tower risk and the aspect risk and the land cover risk and the roads risk and the slope risk here. Everything else should be off. And then on our usual explore button here, so on the map underneath Explore, we want to change this. This probably isn't set for you. I usually set it so to visible layers. Often it's just set for the topmost layer. Let's just change what shows up in the pop-up. So I'm going to click here, and you can see that we got a result of 3 for our wildfire risk, our final risk, and that's because it couldn't be seen by a tower. The aspect is okay, but it's in a high-risk land cover, roads, and slope risk area. So you can do that with any cell and kind of figure out why you got the value you did and kind of check your results. All right, so our real kind of analysis is done. But last thing we want to do here is get some kind of comparative statistics for different areas, for different zones of our map. Those zones would be different mountain ranges or different parks here. So we want to be able to compare one mountain range or one park to another. And to do that, we need to first define those different zones. So I've included those in the exercise data. So that would be the study area parks here. Right? So here's the different parks in those mountain ranges. So we can actually compare each one of these to each other. The way we're going to do this is using a tool called Zonal Statistics. So it gets statistics for a zone, pretty well named actually. And that is going to be inside of our Spatial Analyst tool toolbox as well. So there's a few zonal statistics tools here. The one we want to use is this one called Zonal Statistics as Table, which gives us all the different statistics for each one of our zones. The other statistics tools, you have to pick which statistic. So our zone data is the parks. Okay. The zone field is going to be name, so the results will have the name attached. We're going to end up with a table, so we're going to have to join this back to actually have a layer result. So we'll use this as the key field, so that'll be the name field here. And then the raster that we want to get the statistics for, let's go risk wildfire. The output table name we're going to call park wildfire stats. We're going to keep this all statistics type. I can keep all the defaults here, and we can make sure that this ignore no data in the calculations is checked. Go ahead and run that. And so this is done. You don't get any new layer or anything because what this did was it made a table, Zonal Statistics as table. It's a standalone table, so it goes down to the end of the contents pane. Let's go ahead and open that up and see what we have. So this is for each park with the name of the park. We have the count is the number of cells in each park, so you can kind of use that to figure out area, which is also here. The minimum value in that of wildfire risk, so that's always going to be 0. The max is 4. There's 4 numbers there, so the range is 4. The average, the standard deviation, the sum, and then some other statistics that you have to work with here. For us, I think the one we're kind of interested here is the mean. So regardless of the area, what is kind of the average wildfire risk for that zone? Okay, so this is just a table right now, right? So we're going to have to join it back to the this layer so that we can display it as an actual layer. So this name field will be our key field to do that. So I'm going to go ahead and join that. So I'm going to go right click on join, add join. We're going to use the name field. We're going to link it up, join it up to our park wildfire stats. Hit OK. Now let's look at that attribute table. And so now, because this is joined, we now know for each park all the different stats. So if I click on a park here, we can look and see what the different stats are, which is great that we can click on them, but kind of do something a little bit more interesting with it. Let's use that for symbology. So go to the Appearance tab here, Symbology, and we're going to use this unclassed colors this time. Let's change this to a red color ramp. It's called Reds Continuous. And this is displaying by shape length, which doesn't mean anything right now. We want to use the mean. So this is currently displaying the average fire risk value for each one of those by color, which is great. Again, pretty close here, but let's go ahead and add some labels just to kind of finish this off. So let's label the study area parks. We're going to do that on the labeling tab here. Let's pick instead of, oh yeah, that's fine. We'll go ahead and hit label here just so we can see what that looks like. So right now it's showing the name. We don't want the name. We do want the name. Sorry, looking back and forth at the instructions here. We'll want the name, but we also want to include some other information. So let's do a couple of things here. So we can make a little bit more complicated labels using this expression here. Usually we just pick a field, but let's actually do something a little bit more here. So if we hit this expression, we can actually write more information here to include. So just as an example, let's put name with a colon and a space, and use the plus sign, and I'll hit apply so you can see what that looks like. So that makes a little expression with the name and then the actual name, right? So you can put anything in here, make these nice labels. So what we want to actually do is put the name, and then we'll write this, we'll put the average after it, so in parentheses. So anytime we just have a text string, we have to put it in quotes, just like we did the name there a minute ago. So in quotes, we're going to put a parentheses, or open the parentheses, put a plus sign, and then the mean. Right, so it's going to substitute that in, plus, and then we'll close the parentheses like that. You also put quotes around both of those. Right, I hit apply, and now we've got, you know, the name of the park and the what the risk value is. But you know, you're probably wondering, oh, we've got this long decimal. That's not really helpful. So we can do a little bit more with this expression here. So just go ahead and after the plus sign, so we want to round this mean, so we can use there's a round function to do that. So if we put round here and then open your parentheses, so and go ahead and put it around the end of the mean there, and we can have another parameter here. So if we have a comma 2, so that means that we want to round to 2 digits after the decimal. Okay, so we got round this number with 2 digits. Hit apply. Looks much better to me, but I don't like how they're being displayed. So I'm going to make this just a little bit more elegant here, and we'll pick a different text symbol. Go down here. I want to use this this banner text black with some transparency. It's looking pretty good, but I kind of want to actually kind of offset those a little bit with what I call leader lines underneath this label placement option here. So up here, we go to label placement. We're going to change this, make sure we're on this position thing here. Placement, yours might have already been opened up there. And then instead of horizontal in the polygon, we want to do horizontal around the polygon. And now it kind of does those as call outs for us. I'm a little bit happier with how that looks, and their dynamics. So as we move around, those labels will replace themselves and find a nice spot for it. All right, so that is it. That's our model there. Hope you guys found that useful. It was a lot of good raster tools and an interesting topic. So hopefully you guys got a lot out of it, and I will talk to you guys next time.